So guys, section 3.3, not really a section you guys need to focus on for your final or it's not in your labs or assignments or anything. So I'll go very quickly over section 3.3 and then we will get into section 3.4. Okay.
Sir, before you start, can I ask you one question, please?
Yeah.
I went to PeopleSoft. I couldn't see my mark for the midterm.
Okay, it's there. I put them up last night, so.
I don't know, when you send the email
Yeah.
that you posted, I logged in and it wasn't there.
Yep, they should be there. You'd have to check again. They're definitely there. I put them up last night or even the night before. So yeah, they're definitely there.
Is it under name midterm or quiz?
Test.
Test, huh? Okay, thank you.
No problem. Okay, so yeah, all right. So hybridization, this is kind of a complicated topic, but there's really only one part of this that you need to take away from section 3.3. So I'll kind of skim through the early material, but really the only part of this you need to know is the difference between cis and trans, which I'll talk about today. And it's very easy. Okay, so in chemistry, the hybridization is talking about the mix. Now, okay, first of all, let's think about what the word hybrid means. It's typically a mixture of two things. So think about an electric car, or sorry, a hybrid. Now you can get fully electric cars, but I remember when I was younger, like the Toyota Prius was a hybrid, meaning it ran on petrol and electricity, depending on how fast you went. That was called a hybrid because it ran on electricity and gas. So a hybrid is the idea of mixing orbitals into hybrid orbitals with different shapes. So orbitals being kind of like the bonding electrons around the molecule, but when we have like single, double, and triple bonds, we kind of alter the shape of these molecules. This, if any of you go on to maybe do a degree and you do more chemistry courses in a degree program, you would talk about this a lot more. Hybrid orbitals are basically used for us to talk about the shapes, molecular geometry, and that can tell us the properties of different chemicals. So the way that chemicals are spread across a double bond, for example, kind of will tell you if it is what type of molecule you're dealing with. Doesn't really matter for single bonds. It's more about double and triple. So I'll get into that. So this you might have done in 1121. I know the medical science students do this in chemistry 1200 a little bit. They talk about sigma and pi bonds. Now, again, don't need to know this particular slide, but the idea are sigma bonds are your strongest bonds, head-on, overlapping orbitals of electrons. These would be like single bonds. Sigma bonds are related to single bonds. Pi bonds are formed by sideways overlapping, not head-on, but they kind of align side by side. And this is where you would typically get your double bonds. Again, you do not need to memorize this information. But the way that the bonds are spread across a single bond or double bond can tell me the shape of the molecule and its properties. So there's three types of hybridization that we basically focus on in this course. We have alkanes, alkenes, and alkynes. So I do have like a little typo here. Okay, so if it was sp3, meaning one sigma bond and then 3 pi bonds, this would be a hybridization or a shape that you would see typically in alkanes, like methane. If you had sp2, and again, this is a more condensed overlapping structure. We have a sigma bond and 2 pi bonds condensed. That would be what's called a double bond. So ethane would be an example, ethene would be an example of that. And then if you just had sp1 or sp, that would be two of these sigma and pi bonds overlapping to form a triple bond like Fi. Again, excuse me, not something we really need to worry about for this course. This is kind of just like an introduction, but what we really need to focus on here is slide 35. So alkenes and alkynes, we call them unsaturated molecules. They have different sharing of electrons that relate to sp2 or sp. What this means for you guys is that when I draw a double or triple bond, they're actually planar, which means flat, versus methane, which would be in like 3 dimensions. I wonder if I can show you this. I think I have an app that can maybe explain this a little better. Let me just test something before I share it with you. I should have tested this before, but I just thought of the idea right now. Let me just see. I might be able to do this. Okay, no, I can totally do this. All right, I got an idea. Let me show you what I mean by triple and double bonds being flat, being planar. I'm using one of my favorite free websites. I'll bring it up. I'm going to share my screen in a minute. All right, let's share my screen here. So this is a really cool website. It's called moleview.org. You can see up the link up in my Chrome up there, moleview.org. And what it lets you do is sketch molecules. You can convert them to 3 dimensions, and then you can have a look at them. So let's look at the difference between ethane. All right, there's my ethane. Right, so there's ethane. Let's look at this in 3 dimensions. So if you can see here, it's totally a 3-dimensional shape. We have bonds going away from us, bonds going to the left, bonds going up and down. This is a 3-dimensional shape. Like if you remember 1120, this would be like tetrahedral type of shape on one of the carbons. It's 3D. This kind of goes back to Vesper theory in chemistry 1120. Okay, what about ethene? So there's ethene. I really love this app here. Let's look at this in 3D. And actually, let me just check the chat here. Oh yeah, Naim, I've definitely showed you this before, this app anyways. Okay, look at ethene. Now you might look at this and say, oh, that's 3 dimensions, but look at what happens when I turn it to the side. It's flat. It's hard, I don't know how to rotate it the way I want it, but kind of like this. It's flat. We could lay this flat on a table, right? Imagine if you had this shape. There we go. You could lay this flat. Notice there's nothing going up and down. It's just on a flat plane. And this is all I mean about that hybridization stuff. You don't have to memorize sp3, sp2, don't worry. All I mean is when you bond things, depending on the type of bonds and how the orbitals overlap, you'll get different shapes. And the key is when I draw alkenes or alkynes, I get flat molecules. Look at this guy, it's perfectly straight line. No 3rd dimension in this. It goes left and right, but it doesn't do anything else. So again, if you laid this on a table, it have nothing sticking up off of the table. All right, so again, don't stress too much about SP. Don't worry, I'm not going to ask you about that. But this leads me to talking about some words you guys might hear. Called cis and trans. Sorry, I'm reading and thinking at the same time. So The shape of carbons on a double and triple bond are planar. And if you're thinking of chemistry 1120, which I know you all are because you can remember it, I'm sure, alkenes would take a trigonal planar shape and alkynes would take a linear shape. Don't worry, we're not going to be talking about trigonal planar, tetrahedral. That's all from 1120. So what you guys need to know is this stuff. This is a question I typically would have had on your test last week, but I didn't get it covered in time. This is cis and trans isomers, or the idea of what happens if we have a double or triple bond and we have elements that are on opposite sides or the same side of that flat shape. So I'll explain. We're going to do examples, don't worry. In chemistry, the word cis, and I'm saying that like I'm really emphasizing the cis sound. If I call something cis, it means the elements, the functional groups, the carbon chains are on the same side as the double, or on the same side from the double bond, I should say. So if you laid this object down flat, cis would indicate that the carbon chains are on the same side. Trans, if you think of the word trans, it means across. Like in Canada, there's a very famous highway. It's called TCH1, which stands for Trans Canada Highway, or it's Route 1. And that is a highway that goes across the entire country of Canada, from the East Coast, where I live, all the way to Vancouver on the West Coast. Trans Canada means across Canada. Cis means same, trans means opposite or across. There's not many new terms for you guys left, so this is exciting. All right, so cis and trans isomers, remember what an isomer is. An isomer is a chemical that has the same molecular formula but a different shape. Cis-trans isomers can happen in cyclic groups. Cyclic groups are also flat. It can happen in alkenes or alkynes. But it cannot exist in an alkane. There's no across, because if it's not flat, there's no top or bottom. Think about it like that way. Think about your desk or a table if you're sitting at one now, or even if you're, I know some of you actually listen in your cars, which I don't recommend, but anyways, your car, your table, your desk, it has a top, it has a bottom. Anything flat, like a ring, a benzene ring, an alkene, an alkyne, anything flat has a top and a bottom. But in an alkane, it's in 3 dimensions. There's no top or bottom, because there's actually, you know, a left, a right, an up and down, a backwards and forwards. There's no same side. They can all rotate at any point. A little hard to explain, but again, for anything flat, like a ring or an alkene, you can have a top or a bottom. And that honestly changes how the molecule behaves. So I got a couple of examples here. I got 3, 4, I have a million examples, but maybe by the time I get to slide 40, it might make a little more sense when you see me do this on slide 40. Okay, so let me just explain. I'll show you a couple of examples, and then I hope it will really make sense when we practice one. Let me just check the chat too, some questions in there. No problem if you are late. All right, so this now, guys, between us, I'm not really gonna get you into naming these. What I would typically do is I would give you a molecule and then multiple choice, and you would tell me if it was cis, same side, or trans, opposite sides. Okay, so cis 2-butene, again, you are not expected to name this. So you just need to know the difference. So do not need to name. But you are expected to know which one would be cis, which one would be trans. So here I have a double bond, C double bonded to C, and the methyl groups are on the same side. They are both on the top. Again, think of this like a table. They're both on top of the table. We would call this cis-2-butene. Now, you guys would know that this is 2-butene anyways. It's butene, well, it's butane. Because there's a double bond, we call it butene, and the double bond is on the second carbon, not the first carbon, so we call this 2-butene, no problem. But cis means that they both are on the same side. Trans means they are on opposite sides. Okay, so we have top and bottom. These go across the molecule. Here we have top and top. So this would be cis because it's on the same side, and the other would be trans because it's going across the table, you know, one up, one down. The interesting thing, and honestly, this course doesn't get into it in great detail, but depending on the molecule, like this is a pretty common or basic molecule, but depending on the molecule, these what are called stereoisomers or geometric isomers, because they have different shapes in 3 dimensions, they can have crazy chemical properties. There's like stories of drug trials or doing, you know, medicines used in the 60s and 70s that had really bad side effects because the medicines had the wrong stereoisomer. Really interesting subject, but not something I'll get into with you guys, I don't think. But these can have completely different chemical properties. It's really interesting. And last thing I'll mention, and then I'll show you a couple more examples. The interesting thing is if you made in the lab, now we're not going to do it in this course, but if you made this chemical in the lab, 2-butene, so I gave you some experiment where you would like reduce an element to be 2-butene, or reduce a compound, your mixture, your product that you get from that experiment would have some mixture of these what we call stereoisomers. And it's really one of the challenges in organic chemistry labs is to isolate or maybe remove one of the stereoisomers. Like again, this section, guys, is a, I mean, you could do a whole course on this section. It's so interesting, and you can go really deep down the rabbit hole in this, but we don't need to. So like, let's just look at all of these examples here, like the different ways I could draw the molecule pentene, okay? I could have a straight chain isomer for pentene. 2-pentene has 2 geometric isomers. So this is 1-pentene. But if I had 2-pentene, I could look at where are my groups going in that chain. Again, think of this like a table. Are the groups on the same side? And not that these are groups, but are the carbon chains on the same side? That would mean it would be cis. Or are they across? Trans. Again, top and bottom. So you do not need to know how to name these, but if I gave you these 2 molecules, and I said which one would be cis, which one would be trans, you should be able to tell me that this is cis and this is the other one is trans. Again, for anybody that's confused right now, you'll see this when I do the next, or not this example, but the next example. This one, you should really see this. Okay, last kind of slide about this, and then we'll do practice. Cyclic compounds are also flat, and I can show you. I actually, Naeem mentioned that I've shared this website before, and this is what I think I shared with you. Ring shapes are also flat. So if you guys can see my screen here, okay, let me erase molecule. Let me just put down a ring, any ring. Let's do cyclopentane. So look, there's cyclopentane, nice and pretty. Let's turn it into 3D. So basically flat. It kind of crooks up a little bit, but you do have a top and a bottom to this molecule. A benzene ring might even look a little better. I'll show you a benzene ring in a minute. But there is a top and there is a bottom to this molecule. Let me show you maybe a better one. Let's try classic benzene. This, you'll really see this now, how flat it is. There's our benzene ring. I'm just cleaning it up. We will get into this soon because our next chapter is about benzene rings. But there you go. This is maybe an easier example. You can have like a top and a bottom to this. It's planar. Terrifying. Yeah, I know it can look pretty terrifying for sure. Let's try cyclohexane. Let's see what this guy looks like in 3D. There's cyclohexane. There we go. Pretty much flat, and there can be a top and a bottom to it. There are little crooks in the molecules, like little bends, but that's just the VSEPR theory in action. So if I go back to my notes, new share, again, you do not need to name these, but if I asked you on a test, which one of these are cis and which one of these are trans, it's pretty straightforward. Does somebody have a question? There's a mic going. No question? Oh, and sorry, Naim, yeah, the medicine thing is terrifying. It doesn't happen anymore, I don't think, but you know, very interesting. All right, so this one's a little, this one you guys really need to memorize, or not memorize, sorry, remember chemistry 1120 when, and now I say remember, it's not really that big of a deal, but if you remember in 1120, these types of lines, this means towards you, it's called a wedge. And this means away from you. This is, so think of like top and bottom. The one on the left, we have one chlorine sticking on the up on the top, we'll say, towards me in the cyclohexane, and the other chlorine we have sticking down or away from me. They are on opposite sides of the table. Again, think of this like a flat molecule. So one's on top, one's on bottom. We would call that trans. Cis here, we have both of them coming towards me. If they're both coming towards me, they're on the same side of the table. We would call this cis. And this, I mean, look at cyclohexane. It looks like a table, right? It's like a hexagon-shaped table. And I'm saying if the chlorines are on the top, meaning they're both, you know, facing us or on top of the molecule, we would call it cis. If one's on top and one's on bottom, it would be trans. All right. I was hoping this would be quicker, but it's so complicated in theory that I didn't want to go too fast. But let me show you how kind of easy this is. Okay. Now, you guys don't need, again, you are not expected to name or draw. All you guys need to know is if I give you a molecule, is it cis, is it trans? So we're going to go the extra step here, though. We're going to draw them. All right, first things first, let's draw ethene. So ethene would look like this. Now, in this case, guys, I'm just going to put the carbons in. I know we typically don't, but this might help explain it a little better. So this is ethene, right? Ethene, you would also just draw like this. Okay. The name 1,2-dichloroethene means you guys, if you drew the skeletal structure, you might draw it like this, for example. But the real interesting thing about this molecule is we could also draw it like that. We could have the chlorines on the top or the chlorines on the bottom. You are, again, not expected to draw this, but you will, if I gave you both of those images, should be able to tell me if one is cis and one is trans. So trans means across. So what I'm going to do is on this carbon, I'll put a chlorine on the bottom. On this carbon, I'll put a chlorine on the top. Now there's also a hydrogen here. We don't need to worry about hydrogens, but this would be the molecule. If you did the skeletal structure, it would look like this. This is trans. We have a chlorine on the top and a chlorine on the bottom. Cis would, and I guarantee you some of you guys could draw this for me right now. Cis would be same side. So cis would look like this. If I did the skeletal shape, it would look like this. So again, all you need to do, if I, give you one of these images on a test, and like typically, guys, I will make it look like this on the top, because then you can really see, across or same side. All right, pretty straightforward. Now, this one's an interesting one. Well, I was going to say maybe you guys can try this, but you're not expected to name. Here's what I'll do. I'll get the names for us ready, but then I'm going to ask you which one is cis and which one is trans. So let's do the name first. All of you should be able to name these because this is what your last test was on. So naming shouldn't be a problem. So 1, 2, 3, 4, 5, 6. Remember, you have to number them with the longest chain. These are the same molecules, by the way. They're just stereoisomers. 1, 2, 3, 4. Now, I wouldn't go here. I would go 5, 6. So both of these elements are basically the same. They are 3, 4 dimethyl hex. I should put my number in 3 hexene. Okay, the other one, I don't know why I'm writing it again, but here we go. The other one is also 3, 4 dimethyl 3 hexene. They are the same molecule in terms of name and molecular formula. So these are isomers, but more specifically, they are stereoisomers, geometric. They're different by shape. Okay, so my question for you guys is, this molecule, I have one here. I won't say anything. I'll just say I have a methyl here and I have a methyl here. Is this cis or trans? Are the methyls on the same side or opposite sides? I have one answer from Naim, like Naim did A and B. Does anybody disagree? Or do we all agree that A is trans? Oops, sorry. Right, again, think of the double bond like a table. And I have a methyl group on the top of the table and a methyl group on the bottom of the table. Now I know the molecule is on an angle, but that's just how we draw it. Well, that's how the computer draws it. Abdulaziz agrees. Saud agrees as well. Well, Saud gives me the answers. Yeah, you're right. This would be trans 3,4 dimethyl 3 hexene. Now, again, guys, for the purpose of chemistry 2420, you would just have to tell me the trans part. Oh, as I'm getting a phone call, which is I never get. Just let me answer that really quick. It's probably somebody trying to sell me something. Just give me 1 second. Myself, but I didn't. You guys could hear me. It was somebody trying to sell me something. All right, back to the screen here. Okay, sorry about that. It's just, you know, when nobody ever calls you and your phone rings, you're curious. Anyway, okay. Anyways, we're pretty much done for today. As I think Saud and Naim and Abdulaziz agreed, this would be same side of the table. So this would be cis. Again, if I gave you this on a test, I would say, you know, here are two molecules, A and B. Which molecule is trans, or which molecule would be called cis? Phew, I really thought that wasn't going to take as long as it did, but you know what? I guess that's just kind of like the nature of section 3.3. If there's one thing to take from today's class is if I gave you an image like these two images here, you should be able to tell me which one is cis and which one is trans. That's it. All right, pretty easy. Now, this is exciting. I'm done. I'm obviously not going to do anything else because we don't really have time. This section is so important. This is the end of chapter 3. This section here, so important. And it's actually a little challenging, a little difficult. We're going to look at reactions of alkenes, dienes, and alkynes, or well, more specifically, we're going to look at reactions of alkenes and alkynes. Funny enough, we actually did a little bit of this in lab 4, but I had to help you along because we didn't make it as far in the course to do lab 4, which happens every semester, so not a big deal. But we will look at 5, I think maybe 5 different reactions of alkenes, and it can look intimidating, but it's actually really, really interesting. So we're going to do that or look at this tomorrow. We won't do it today. This might take us a class or 2. I'm looking at it now. It'll definitely take us probably 2 classes, but it's not that bad.
Check.
Okay, I'm done. 1 second. I'm done with the new information. So I'm going to hit stop record now. But if there's any questions, like I think I have one student, let me know. Okay, go.